So I started the recording, and I've already got the screen up because I want to just go ahead and get right to it. So remember that at the end of the day, we're trying to finish up some thiol business, do some reactions and some mechanisms that involve thiols. And then what I want to do right after that is move straight into the next chapter that's not NMR IR mass spec, and that's going to be conjugated dienes. And so we'll have enough to go all the way until class period is over for the day, and we'll get through it, and then we'll see where we're at, and we'll go from there. So as I was saying, we were leaving off with thiols, and so we remember, if we recall, a thiol is something that has an SH on it, and there's a couple of different ways we can make thiols. And if you remember from Organic Chemistry 1, that the SH group is a very good nucleophile, but it's not a particularly good base. So it easily does a substitution reaction where it kicks off the bromine, and even if it's in, say, a secondary position, you can still get, and of course this might be in ASH as well, you can still get the sodium sulfide to kick off the bromine and do a substitution reaction. Don't forget about your stereochemistry. Recall that the SH ion is not a particularly good base. So this is some ways, these are the primary ways we have to make these molecules, and there's not much going on here with formation of thiols other than these reactions. But we do immediately get into the reactions of thiols. And thiols, if I have two of them, they can form a disulfide. And disulfides are cool because they're a particularly common functional group when it comes to proteins. Oops, excuse me. And this is going to bring in our first mechanism, and it's going to have some similarities with other mechanisms that we'll do here in a second. If I take the thiol and I react it with sodium hydroxide, the hydroxide is acting as a base, and it removes the proton and ultimately forms an S minus. The S minus then goes along to react with that bromine and form this really interesting species that has a sulfur attached to a bromine. And now I've got a nucleophilic sulfur ready to attack the other one. Now this is already deprotonated through the action of the hydroxide. And so it's ready to attack that sulfur and kick off the bromine. And that's what makes our disulfide bridge. And if any of you are interested in the proteins in your hair that make hair curly, are disulfide bridges, and they're formed reversibly through the action of these reactions are reversible, and these disulfide bridges form and break and then reform within the proteins of your hair. And if you have curly hair and you take a shower and you notice that your hair isn't as curly anymore when it's wet, some of the disulfide bridges have broken, and then as the hair dries, some of those disulfide bridges reform. So, interesting factoid of chemistry there. Okay, any questions with that little bit? I want to keep going with that, because once you got a disulfide bridge, we can do some chemistry with it. And this is a zinc and HCl, another one of these reagents that we're going to see several times this semester. And so, what do you think? What do you think is zinc and HCl going to do? Have we run across this before? What do neutral metals tend to do? What kind of chemistry? Well, if you said they reduce, then you would be right. That I know that I'm getting all sorts of responses in the chat, so many that I can hardly keep up. So I just want to then ignore them all since they're just too much. It's a reducing agent, right? And so if you think about platinum catalyst or palladium or with mixed with H2, then you'll find that these metals then are activating some of these reduction processes. And when you see zinc and HCl, that's essentially what it's going to be doing from this point forward. It's going to be doing some sort of reduction. So a disulfide bridge in the presence of zinc and HCl will break into the respective sulfides. Okay, let's see. And then we can then, sorry, these aren't sulfides, they're thiols. A sulfide is the analogous situation when you have a thiol ether. It's the analogous situation for an oxygen ether, except unlike the oxygen ethers, they are reactive. And you can take, I'll show you some of the reactions of them in a second, but in order to form them, we take a thiol, let's make it R prime. We react it with sodium hydroxide, and we already know what happens with the sodium hydroxide is that it forms a negatively charged sulfur, and the negatively charged sulfur then acts as a nucleophile to form that bond. All right. Let's just review. Hydroxide deprotonates this guy. I've now got an R minus, and that reacts with the Rx in a substitution reaction like I might expect with a halogen group. Okay, now the thioethers or the sulfides, unlike their oxygen counterparts, are somewhat reactive. Specifically, they can undergo oxidation. Again, we're going to talk about some reagents that are common oxidizing reagents, and you want to be able to recognize them going down the road, because just like zinc and HCl will always be doing some kind of reduction, just like H2 and platinum catalyst always does some sort of reduction, just like lithium aluminum hydride and sodium borohydride do some kind of reduction, just like sodium dichromate will always do some sort of oxidation. If you see sodium periodate, you'll know that sodium periodate also is an oxidant. What about this? What do you think this is? If you remember back when we have hydroboration oxidation for the anti-Markovnikov formation of alcohols, the second step involves hydrogen peroxide and sodium hydroxide. So the hydrogen peroxide in that second step is the oxidant that's doing the oxidation in hydroboration oxidation. So this is also an oxidant. It turns out that this one in this case is the stronger one. And compared to H2O2, this one's a little bit weaker. So if I react a sulfide with H2O2, I will add oxygens onto the sulfur as much as the sulfur could possibly stand having oxygens. If I react a sulfide with sodium periodate, then I only add one sulfur or one oxygen to the sulfur. Now I can go along and react this with H2O2 and reform the sulfone. Okay, so what I want to do is I want to just pause real quick and just kind of review the stuff that we did. We essentially learned one new mechanism. That's sort of, that's still on the screen. If you take a look, the one new mechanism that we learned is right there. That's the one that does hydroxide, doing proton transfer and forming a negatively charged sulfur that can then act as a nucleophile. We saw how that nucleophile can then react with bromine and attach itself to a bromine, and then later on that's going to leave that sulfur itself ready to be attacked by another nucleophilic sulfur. If we take the proton off the sulfur again in a different reaction, then it can react directly with an alkyl halide and form a sulfide. Those are the only two mechanisms that we learned, but we did learn a couple of reactions. Some reviews of reactions, and again, maybe you can't see them at this point, but they're still up here. They're the substitution reactions of alkyl halides that produce thiols. Then we take thiols and we can create disulfides, and then we also showed how we can react a disulfide in the presence of a reducing agent and turn them back into thiols. The last thing that we did then is discuss the formation of sulfides and then reacting sulfides with oxidants to form these sulfones. Does anybody have any questions about that before we? R just means any R group, any carbon chain, and remember, if I just put R prime, then all I'm saying is that it's different, that this R group is different than this R group, and it's just a way to show that, just to show that there could be some differences there, right? We want to all I'm doing is just kind of pointing out it doesn't have to be the same thing. Any other questions? All right. Okay, and so like I said before, I'll come back along and I'll create some videos that help us review the topics of NMR, IR, and mass spec. Certainly from NMR and IR, you should know that from Organic Chemistry 1 when it comes to the learning that I expect you to have achieved at this point in your organic chemistry career at our school. Now, I realize that that's different in other schools, and so that's why I want to go ahead and create some review videos so that you can take a look at that. So let's move on past that. Let's move on to the next chapter that's going to be important for us when it comes to organic chemistry. And that's moving on into conjugated pi systems. And there's a lot of interesting chemistry and a lot of actually molecular orbital theory that we're going to have to remember from Organic Chemistry 1, or at least remember how to apply it. Potassium permanganate is another oxidizing agent, although I'm not sure how it's related to this. Yes, thank you. I'll disregard. Okay, so what we're talking about right now is conjugated pi systems. So this is the section we're talking about. Conjugated pi systems. And then ultimately there's a whole class of reactions that we're going to study called paracyclic reactions. And so let's think about what we mean by conjugated pi systems. And let's start off with a diene. And what does a diene mean? It means a molecule that has two double bonds. So how could we see those double bonds? One way we could see them is if they were, and this is very rare, to see them directly across or attached to the same carbon. So that's one way, and these are called cumulated double bonds. Just like your final in this class is going to be cumulative of all of the material you've learned up to this point. Here is a situation where they're conjugated. This is conjugated. And you should become familiar with this pattern. So it's the alternating double bond, single bond pattern that is conjugated. And all of the things that we're going to study from a chemistry perspective will involve conjugated double bonds. Now, there is another situation where we could have a diene, and here is a diene, but in this case, they're not conjugated. These are isolated. And the reason we say that they're conjugated is because there actually is some resonance that we could show. It's not a perfect resonance structure, or in other words, it's not an equivalent resonance structure, but we could show one like this, where there's a negative charge here and a positive charge there. And of course, we could have shown the electrons moving the other direction. In the cumulated and isolated situations, that resonance isn't there. Again, it's not an equivalent resonance structure, but it is a resonance structure that can be shown without violating any octet rules. And so this is what we mean by conjugated. This pi system allows some sort of resonance to take place. We could see this happening in a conjugated enone as well. We could say, well, this system is conjugated as well, and we can show the resonance happening here. Where the negative charge appears on the oxygen and a positive charge appears on the carbon. All right, I'm gonna just pause just for a quick beat, see if anybody has any questions. So what we're talking about are conjugated double bonds, and these are specifically, in this case, I'm talking about dienes, but we're gonna move past dienes and talk about trienes and tetraenes, things like that. Enone means I've got a ketone and it's got an ene in the one position over. It can't be like this, right? I can't have this situation because that violates the octet rule. So an enone is having a conjugated double bond, or a pi system in a double bond conjugated with a double bonded oxygen. That's the one part, and the ene part is the double bond between the two carbons. Does that help? Cool. All right, so let's see, how could I make these things? Well, again, this is a review of some chemistry that you already know. If I take something that has a double bond like this, and I react it with T-butoxide, reacting it with T-butoxide prevents the substitution reaction that would be in competition from happening. I can form a doubly conjugated pi system this way. Another alternative would be to have this system form a conjugated diene, and this is a little bit new. Now, of course, remember, if this thing is reacted with a very strong base like sodium amide, it doesn't form a conjugated double bond, it forms a triple bond instead. Okay. So let's think about this thing as well. I could have it in this configuration, or I could have it in this configuration. This is called S-cis, and this is called S-trans. In other words, cis-like and trans-like. Can you imagine if one of these is more stable than the other? And can you think of which one is more stable and why it might be stable? Just take a quick breath and think about that just for a second. And type in chat, what do you think? Which one's more stable, the cis or the trans version? And if you think so, why? Yeah, there we go. Remember, there's not a whole lot of answers in organic chemistry, and it is indeed the trans version. And the reason is steric hindrance. It's one of our go-to answers. Remember, again, there's not a whole lot of answers. Steric hindrance is a very common explanation for why things are. Resonance is another explanation for why things are the way they are. Looking in the mechanism and looking at the different different energies of the intermediates is certainly another reason. And they both have the same ability to do this resonance that we were talking about. They're both conjugated, and so there is some resonance going on, but the resonance is equal in both cases. So that's not like one of the reasons we would be looking for in this particular case. In this case, it really is just the steric hindrance provided by the two groups that are facing in the same direction versus the two groups that are sort of facing opposite directions. The trans group is a little bit lower in energy than the cis group. All right. Now here's where I get back into Orgo 1 and I do some molecular orbital theory. And I'm going to just give you a warning. You're going to hate this part. You're going to hate this part because we're going to expand. We're going to start simply and we're going to expand it. And you're going to hate it because you thought you didn't need to worry about it at the beginning of Orgo 1. And in fact, most of us don't really go too deep in it in Orgo 1. But it really becomes crucial in Orgo 2. And we're going to try to go through this molecular orbital theory, talk about a pi system, and then we're going to talk about a conjugated pi system, and then we're going to talk about the triene, the 3 double bond conjugation. We're going to draw out all of the different molecular orbitals that are created in the system. But then what we want to do is we want to look at some chemistry and look at how the molecular orbital theory explains stereochemical outcomes of some of these reactions that we've been hinting that we would be doing, these pericyclic reactions. And so the first thing I want to do is sort of remind you, if I have two atoms, and let's say that we want to combine some p orbitals. If I want it, one of the rules that we need to remember about combining orbitals mathematically to come up with another mathematical description of orbitals, and this is what we're doing. We're taking atomic orbitals and we're combining them into molecular orbitals. It's a mathematical process, and you can do this explicitly with some linear algebra and some other approximations. But we can do it in a sort of qualitative way in organic chemistry by just invoking some rules about symmetry. One of the things that we want to invoke, another rule about symmetry, is an energetic symmetry. Remember that these are essentially energy graphs. And if I have two orbitals and they are at a particular energy level and I want to combine them into a new type of orbital, and I want to just draw some lines to kind of designate the space between, this is atomic orbital space and this will be my molecular orbital space. Then that means that the orbitals that we put in the atomic orbital space have to sum to the same energies in the molecular orbital space. And so what that means is if I get two orbitals in, then I get two orbitals out. But if they are the same energy, we end up with one that goes down in energy and one that goes up in energy in exactly the same way. How is this better mathematically? Well, if I start out with a single electron in each of the two orbitals, the energies of the electrons in total are lower in the molecular orbital situation. And so this is one of the ways that we justify having the ability to mix up these atomic orbitals mathematically to make molecular orbitals. At the end of the day, we're showing you a configuration that's lower in energy. So how do we explain bonding? Well, we come up with some orbitals that can expand more than one atom, and we show that they're going to be lower in energy, thus giving you a physical reason why they would do this in the first place. One of the things that you have to do, though, is you have to be able to take a picture of an orbital, and I'm going to actually draw it on the atom. And you have to combine the picture into its resulting molecular orbital. And this is the part that there's a pattern with that you want to be able to become familiar with in order to do these combinations. If I want to draw the picture of the orbital that, the molecular orbital that forms there, and the molecular orbital that forms there, there's another bit of symmetry that I want to invoke. And it's about nodes. Remember that nodes, a node is a place where there is no electron density. It's a infinitesimally small plane in between the two atoms where there will be zero probability of finding an electron. As for each, or when I combine orbitals, I'll start with the number of nodes equaling 0, and then the number of nodes goes up. When I'm combining these p orbitals, they go up by 1 each time. So since I'm only combining 2 p orbitals, I get 2 molecular orbitals out. Again, 2 orbitals in, 2 orbitals out. One goes low in energy, the other one goes higher in energy. When it comes to being able to draw the resulting molecular orbitals, then I want to think about how to draw that based on how many nodes there are at each of these energy levels. And so let me show you what happens. In the lower energy case, the 2 individual p orbitals combine so that their phases are in the same position. If they combine so that their phases are in the same position, then they combine constructively. And it is perfectly analogous to the idea of them being waves, and waves being able to combine constructively and destructively. If I combine them in the direction where they're out of phase, then the waves are combining essentially destructively. And I just want to create a slightly better picture. And there ends up being no overlap of the orbitals between the 2 atoms. What I'm showing you in the case here is that there's overlap between the 2 atoms in the new molecular orbital, and this is where the electrons reside. This is showing you some bonding. And in fact, all of the orbitals that form below this imaginary line are called bonding orbitals. And so this one would be a pi bonding orbital. All of them that form above the line, so below the line is bonding, above the line is anti-bonding. And so an orbital where the phases are combined destructively is an anti-bonding orbital. It's not that electrons can't be in an anti-bonding orbital. It's just that if there are electrons in an anti-bonding orbital, then they don't help hold the 2 atoms together. Okay, and so this should establish the basic pattern. And so what I want to do now that I've established the basic pattern is take this pattern and apply it to our simplest conjugated system, butadiene. So if I take butadiene, remember that there's going to be an unhybridized p orbital on each of the carbon atoms. And I can represent those 4 unhybridized p orbitals on each of those carbon atoms, 1, 2, 3, 4, combining to form molecular orbitals. So here are my unhybridized p orbitals. And I want to combine them to make molecular orbitals. I get 4 orbitals in. So that means I'm going to get 4 orbitals out. 2 are lower in energy, and 2 are higher in energy. So let's go through this exercise, because this is something that you're going to have to be able to do to sort of draw the resulting molecular orbitals. Let's take the case where I have all 4 of the atoms. And remember, how many nodes will there be at this location? How many nodes will be here? So let's take a look at what is now the inset. What I said is the number of nodes starts off at 0, and it moves up by an integer number each different level of molecular orbitals. So it's still going to start off with 0 nodes there. Here it'll have 1 node. Here it'll have 2 nodes. Here it'll have 3 nodes. And remembering to invoke the symmetry of nodes helps you draw the picture. Now take a look at the inset. The lowest energy configuration involves all of the p orbitals combining in phase. And that's exactly what's happening in the lowest energy configuration in this molecular orbital as well. 1, 2, I'm going to move it up just a little bit. 1, 2, 3, 4 atoms in a row, combining so that each p orbital lines up in phase with the blue on the bottom and the red, or the blue at the top and the red at the bottom. So what would the resulting orbital look like? The resulting orbital would have electron density that spreads across all 4 atoms. If I have electron density across all 4 atoms, this is the single most successful or strongest type of bonding that I could have between these 2 electrons. Remember, I'm going to eventually end up with how many electrons in this pi system? I've got 1, 2, 3, 4 electrons. And so I've just populated 2 of them in this orbital. Let's do the same thing for the next set of orbitals. 1, 2, 3, 4 atoms. But remember, there's going to be 1 node. And when you draw nodes, you want to draw them symmetrically. So the first location to draw a node so that it's nice and symmetrical would be right down the middle. And you're going to end up with the same situation, except there's going to be a change in phase once you cross the node. Just coloring in my pretty orbitals here. Nice, pretty orbitals. Happy, happy little orbitals. Oh yeah, we love those. So Chelsea asked the question, why does a node trigger a change? And so this is a question that's essentially rooted in the mathematics. And the answer to what I think you're getting at the heart of it is really beyond the course. At the end of the day, what we know about the way that we mathematically, because we're taking atomic orbitals and we're doing what we call a linear combination of atomic orbitals, and we're forming molecular orbitals. This is, to put it bluntly, some math tricks. They're just it's mathematical operations on the functions that represent the atomic orbitals and combining the functions that represent the atomic orbitals mathematically to come up with new functions, and then those functions represent something now that we're calling molecular orbitals. Because of the way that we do that math, we know that this pattern with the nodes will come out the same way every time. We'll get 0 nodes at the lowest energy orbital, and we'll get 1 node, the next one, 2 nodes at the next highest level, 3 nodes at the next highest level, and so on and so forth. Until at the very top of the energy chart, you'll have 1 less node than you do atoms. What else falls out of the math is that the phase changes when you move across the node. The phase changes from left or not. Now, I don't think that actually answers your question why, but again, the answer to that question why, I think is sort of beyond the class, and it's buried in that mathematics. Can you at least trust me at that point? So it is just a little bit of it does trust me, thank you. It's just a little bit of hand waving, but it is some mathematical hand waving. And unless you're really good with calculus and linear algebra, I don't think we're going to get into it. So let's show this next combination. How many nodes should there be here? In this case, we should end up with 2 nodes. And so this is where it comes in to be a little tricky, and that you have to think about symmetry. I could have 2 nodes right here, 1, 2, but that leaves a big space here and 2 smaller spaces there. That's unsymmetrical. That's not the way it's going to happen. I could have 2 nodes here, 1, 2. Again, that's not symmetrical. It's not going to happen that way. So let's think about how I can do 2 nodes in a way that is symmetrical. I think if I put a node here and I put a node here, then the picture that I'm left with is symmetrical. And this is in fact the way it looks. And so I'm just going to be consistent. I'm going to start with blue on the right, or excuse me, blue on the left. So that means blue goes up on the left, red goes down on the left, and then I'll just shade in my orbitals. Nice, pretty orbitals. Very happy to be shaded in. Very happy to have some color coordination going on here. And so I've got electrons. The 4 electrons are filling in these orbitals. And so I have a name. These, of course, are the bonding orbitals. We talked about that already. These are pi bonding orbitals. All of these orbitals will end up being pi orbitals, but they're going to be anti-bonding orbitals. And I have a special name for this orbital. This one is the HOMO, the highest occupied molecular orbital. The HOMO is the highest occupied molecular orbital. Enough of that, Karen. The HOMO is the highest occupied molecular orbital. That means I've got a name for this one. Yeah. Oh, and it's not LOMO, it's LUMO. I spelled it wrong. Let me go back. It's LUMO. Yeah, LUMO. What do you think this U is? If O is occupied, what is U? Unoccupied, exactly. And it's the lowest unoccupied molecular orbital. So what do I mean by highest? Remember that this is an energy graph at its heart. What I mean by highest is it's the highest energy orbital where there's electrons. So that's the HOMO. What I mean by the LUMO is the lowest unoccupied molecular orbital, the lowest in energy where there aren't electrons. And so that's what a LUMO is. And so let's finish this out. Let's go ahead and let's make this last orbital. 1, 2, 3, 4. Now, what does this molecular orbital look like? Now, this is the situation where I'm going to have how many nodes? I'm going to have 3. And so the only way to get 3 nodes symmetrically is to have one in between each atom. And so just to be consistent, I'm going to start it off like this: blue, 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 blue. This is the situation where none of these p orbitals line up in phase. None of them. None of them. And so at the end of the day, now you've drawn your full picture of the molecular orbital space from butadiene, from this molecule. It's got 4 pi electrons conjugated across 4 atoms. So I'm taking 4 unhybridized p orbitals and I'm showing how they can combine into molecular orbitals. What we want to be able to, ultimately we're going to use these things to explain stereochemistry. And so we're not going to get to that point today. And so for the last thing that I want to do is take this whole idea, just want to shrink it up into the corner so it's still there for us to think about in just a little bit. But then instead of using butadiene, I want to use hexatriene. So instead of having 4, I have 6. And so I want to take 6 unhybridized p orbitals and I want to combine them together to make a series of molecular orbitals using all the symmetry and combination rules that I just established in the previous example. So I'm going to go a little bit faster. But at the end of the day, I've got 6 orbitals in. That means I should get 1, 2, 3, 4, 5, and I'm just going to move it up just a little bit. I should get 6 orbitals out. 1, 2, 3, 4, 5, 6. What do we know about these orbitals at the top? They're going to be anti-bonding orbitals, and these are going to be pi bonding orbitals. How do I combine them? 1, 2, 3, 4, 5, 6. Well, I know that this one will have no nodes. So this is the situation where they all combine constructively. And just for time's sake, I'm going to do a little bit less of a good shading job. So they're still happy, but they'd be happier if I spent another little bit of time doing some shading, but I'm not. Okay. So let's do the next one. How many nodes should it have? 1, 2, 3, 4, 5, 6. It should have 1 node. It's going to be symmetrical, so that means the node is going to be in the middle. So that means these 3 atoms are connected. Those 3 atoms are connected constructively. And remember, the phase changes. So the phase changes. All right. How many nodes in the next one? So we went from 0 to 1 to 2, and that's where we're at. We're at 2. So how do I set this up? Well, we haven't done 2 yet, so we're at 2 now. The next one up will be 3. So how do I do 2 and make it symmetrical? I'll have a node there and a node there. That means that I'll alternate every pair. So starting with blue, 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 then red, 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 red. Spend just a second shading them in. Oh, you know what I could do? Look at that. Oh yeah, that's nice. Look at that. You can even go back and do this now that I've done that. Oh, now they're really happy. Look how happy that is. So happy. Oh yeah. All right, so now's your chance. How many nodes in this picture? 1, 2, 3, 4, 5, 6 atoms. So yeah, now we're at 3 exactly. And so this is the one that is a little bit of a challenge. And so this is what we want to remember. I could do 1, 2, 3, but that's not symmetrical. I could do 1, 2, 3. That is symmetrical. Do you see that it gives me 2, 1, 1, 2? That's symmetrical. But there's another choice. I could do 1, 2, 3. I could do it this way. Yeah, and this is what we want to do. We want to do this version. And so you know how you know which one you want, because the version that has the larger electron density groups in the middle is the correct version. So this is the pattern of nodes that we want to use. So that means that at the end of the day, it's going to be blue on 1. I'm going to have blue on 2 there, blue on 2 here, and blue on 1 there. Red there, red across these 2, red across these 2, and red across those 2. And so now I can, oh yeah. Somebody said that I was a dork. Look how happy these orbitals are now. They're so happy. They've never been happier. They're like those little trees. They're just like those little trees. Now they're so happy. Everybody loves full color, right? Yeah. All right, let's do these last 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This one at the top should be the easy one, right? Blue, 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 blue. Oops. Blue. None of them line up constructively. And so this was 1, 2, 3 nodes. The next one in the up needs to be 4 nodes. So how do I do 4 nodes so that they're fairly well symmetrical? Again, using this idea that I'll keep the large electron density in the middle. We'll do 4 nodes this way. The alternative would have been 1, 2, 3. Oh, that's 3. Sorry. Oh, there's only one way to do 4 symmetrically. 1, 2, 3. That's 3. Yeah, so turns out there's only one way to do 4 symmetrically. So let's do it that way. So it's 1, 2, 3, 4. 1, 2. Now I can finish this one out while I'm here. just get a little bit better with this. All right, so now that while I'm finishing filling them in for color's sake, think about which one of these things are the HOMO and which one of these things are the LUMO. Which one is the lowest unoccupied molecular orbital and which one is the highest occupied molecular orbital? And when we think about that, we want to think about how many electrons that are in the pi system that we're putting into the molecular orbitals. Yeah, the top 6. Well, the top 6, I'm not sure what that means. Just 2 dots in the middle. You mean these 2 dots right here that are sort of just kind of out of in there? Got those taken care of. So if I have 6 electrons to put into the system, from the 3 double bonds, then I put them in order from lowest energy to highest energy. So that makes this one the HOMO and this one the LUMO. One, two, three, four, five, six, 6 dots in the middle. 1, 2, 3, 4, 5, 6 with 1, 2, 3, 4, 5 symmetrical nodes. Yeah, this whole set is anti-bonding and this whole set is bonding. This whole set is the pi anti-bonding set, and this whole set is the pi bonding set. And this little star signifies anti-bonding. And so there's one last thing I want to do before I put it up and we move on to explaining what's cool about this when it comes to explaining chemistry. What happens if I interact this pi system with UV light? So I'm going to get some UV light and I'm going to interact with it. What happens is that it takes an electron and it excites it. It excites that electron to the next orbital up. So when I think about it, what we're going to call this now is we're going to call this is the ground state. And what would we call this then? This is the excited state, where we have, yeah, exactly. We have 1 electron promoted from the HOMO to the LUMO. And now essentially this is the HOMO. The highest occupied molecular orbital has now gone up 1 step. And this is going to have some consequences in stereochemical outcome when we talk about these cycloadditions or different reactions. And so what I'm going to do is I'm going to stop right there because I think it should be, yep, I'm even 5 minutes past.